Hello and welcome to my second tutorial about PrePoMax. This time I will show you how to perform a torsion analysis in the software. As an example, I will use an elliptical bar subjected to torque. Just like before, the first thing we have to do is to create a new model and select a unit system. In this case I will use millimeters just like before. And now, since the new model is created, I can import the geometry. And also, like in previous case, I prepared the geometry in FreeCAD. And I exported it in a universal file format for import to PrePoMax. This is the step file here. And now, since the geometry is imported, I can create a mesh. So let's go to the mesh tab, meshing parameters, and I will define a maximum element size of 15 millimeters. Now I will hit the preview button to see how the mesh will look like after it's generated, and then I will confirm this. Let's create a mesh now. It shouldn't take too long. As you can see, the mesh is now created and the software automatically switched to the second tab where we can prepare the whole analysis. In this case, I will start by creating a reference point for rigid body constraint. This is necessary because nodes of solid elements don't have rotational degrees of freedom, and that's what I mentioned in the previous tutorial. And because of that, it's not possible to apply torque or enforce rotation directly to those elements. However, we can easily handle this by applying a torque using rigid body constraint. And the other two most common applications of this constraint are modeling rigid parts and applying remote loads, but in this case I will use it to apply torque to this elliptical bar. So let's create a reference point first. We have to provide coordinates for this point, and this will be located here, and the default selection is the start of the coordinate system, so I will just add the distance here to make this point appear at the other end. Okay, so now the point is created and I can define the rigid body constraint. This is available here, and there are two types of constraint currently available: rigid body and tie. In this case I will use rigid body. The reference point is already selected, so I just have to select the region to which this constraint will be applied. I will choose the face here. Now I can confirm, and the rigid body constraint is already created. Okay, let's rotate the part to the other side, and now we can proceed to the remaining definitions. Now I will define the material, just like before. Let's use elastic material properties. This will be steel again, so I can rename it. Of course it's not necessary, but it's a good practice. So I will confirm this, and now let's create a section, a solid section applied to this part right here. So I will choose the part and confirm. The section is already applied, as you can see. We have the constraint also defined, so what we have to do now is to create the analysis step, and this will be static step just like in the previous tutorial. So I will leave the default selections here, and now we have to create boundary conditions and loads which are necessary to simulate this. Let's start from boundary conditions. In this case this will be just fixed boundary condition at this end here, so I won't use the displacement rotation one, even though I could use it and simply constrain the three translations here. This will be the same, but it will be faster to just select this face and apply fixed boundary condition, which will fix all the available degrees of freedom for this model. Okay, let's do this, and now we have the boundary condition defined. Let's rotate the model again to see the other end, and I will define the load now. In this case, before we use pressure, in this case I will use moment to apply torque to this reference point. So in this region type selection I will choose the reference point name, and this will be automatically selected to the only available reference point we have here. And now I have to define the torque. The conditions for this analysis are shown here. Again, I will also show this sheet later on, because here are the analytical results, but for now let's focus on the input data. So here we have the dimensions of this model, material properties, and torque necessary to achieve the desired results. Okay, so let's input the value here. This will be in newtons times millimeters, so I will provide the value in the correct unit. Okay, let's confirm this, and now this symbol here shows how the torque will be applied to the part. Now everything is defined. We could submit the analysis and check the results. But there's one more thing that I would like to do, and I would like to show you. Since we already have the rigid body constraint here, we use it to apply the torque. We can also use it for another purpose. We can define a history output, which is basically output for selected part of the model, selected nodes, elements, or contact pairs. This will be discussed later on. And this history output is in form of XY plots. You will see, or actually tabulated data. So we can request node output and select the, if as a region type we can select the reference point, it will be highlighted here, and as a variable to output you will leave the default selection, which is U, that stands for displacements. Let's confirm this, and then you will see how we can use this history output to obtain the angle of twist for this model. Everything is defined, so I can submit the analysis now. It shouldn't take too long because the mesh is not very fine. Of course, in your case, you can use finer mesh if you have powerful computer, and if you don't mind waiting a bit, it's not a problem to use finer mesh. You will get better results, of course. So it already accomplished the analysis, so we can proceed to results. And here you can see the deformed shape of the model. And now let's focus on the results. Let's verify them using analytical values. So let's start from the stresses. We could use von Mises stresses, but analytical solution is for shear stress, just the one component of the stress tensor. So let's go directly to the shear stress. We can rotate the model. It looks better this way. Of course, we could also turn off this deformation, deformed shape. It's not a problem to go to post-processing and switch this to either true scale or completely off. If you don't want to see it deformed like that, or you can provide your own scale. Anyway, here's the result of the shear stress, and you can compare it with the value here. It's pretty close. Of course, with finer mesh we could get even better convergence of the result, but it's not necessary here. I just want to show you that the results are pretty good even with not so fine mesh. Okay, so we verified the stresses, and now I would also like to verify the rotation angle of twist. It can be done directly because, as I mentioned, the direct results here of displacement, you only have translational ones because of the limitation of solid elements that don't have rotational degrees of freedom. But you can use the reference point, which has the rotational degrees of freedom, to output the angle of twist. And when you extend this tab, you will see that there are translational degrees of freedom as well as rotational ones. We are interested in the rotational degrees of freedom, and particularly in this one because it's the z-axis. So if we click this, we will get a single value for just the end of the analysis. And here's the value of the angle of twist, and we can compare it with the analytical value, which is shown here. Again, you can notice very good agreement of the results. It's almost perfect, of course with some small difference, but it's typical for finite element analysis, and their mesh dependence causes stuff like that. But for comparison with analytical values, it's a really good agreement. Okay, that's it for this second tutorial. It was quite fast, much faster than the previous one, because in the previous one I also had to give you some insight into the software and tell you something about PrePoMax in general, how it works and how it can be used. And here I just wanted to show you one of the most common types of analysis, and actually one of the most misleading types of analysis, because people often wonder how they can perform such analysis in FEA software due to those limitations of solid elements nodes. They don't know how to apply torque, which is a very common issue. And actually in some of the open source codes it's not possible to do this, to apply rotation and torsion to model this like that. But in PrePoMax and CalculiX it's not a problem. You can easily model this using rigid body constraint, which is very handy. Anyway, that's it for this second PrePoMax tutorial. Thank you very much for your attention. In the next videos I will show you the other features of this software. Feel free to ask any questions and suggest topics for future tutorials in the comments. Also have a nice day, and see you in the next video.